Hello again, AP Calcers. Time for lesson 3.6 called the chain rule. And I think you'll find this is one of the most widely used rules of derivatives that we'll have. As you can see, this looks a little bit goofy when we first look at it. Now this FOG, that's this composition of functions. So in a sense we have two different functions, f of x and g of x, and we are looking at them at one time or together in order for us to perform this differentiation. So what this is really saying is that if I'm trying to find the derivative of this composition, this is another name for f of g of x, I first of all will take the derivative of the f, or the outside, and then multiply that by the derivative of the inside. So usually when we've thought of order of operations and whatnot, we work from the inside out, and especially when we even do composition of functions, it's from the inside out. But the chain rule is the opposite. It's from the outside in. So here's an interesting little diagram that you may want to copy down. The f of g of x, so first of all we take the derivative of the outer, they call it the daughter, I suppose, the d of the out, daughter, and then the derivative of the inner, dinner. So we got daughter and dinner. Maybe that'll help you remember it a bit. But I think some examples and just doing plenty of problems on the chain rule will help you get more in the swing of things. Alright, here's our first couple examples here. So let's take a look at these. I'm going to check my pen color here, and we'll just try this. Yes, okay. So trying to find the derivative here, dy over dx. So again, as you can see, maybe the two functions we have here would be the cosine of x, and then of course what's in the parentheses here, x squared minus 2x. So according to the chain rule, we would first of all take the derivative of the outside, and the outside one would be the cosine. And so we know that, whoops, I can pause this. Alright, I think we're back online here. I was just interrupted a little bit by Mrs. Barkey wanting to give me some money, so I will of course always take that. So here we go. So the derivative of the outer, we know that the derivative of cosine is negative sine, and then I don't do anything at all with the inner part. So I just leave that as x squared minus 2x. So there's my outer, or daughter as the previous slide said. But now I want to multiply that by the derivative of this inside part. And in this case it's going to be 2x minus 2. And there's my derivative. That's called the chain rule, interestingly enough. Alright, let's take a look at the next example here, see what that looks like. The derivative of this, again the outside part, we could think of this as x squared. So the outside part, then I'm going to use that exponent, 2 times 1 plus the sine of 3x, and then my power goes down to the first power there. So that's the outer part, and then I want to multiply that by the derivative of the inside. Well, the derivative of 1 of course is just 0. The derivative of the sine of 3x, well, here we're going to have a chain rule within a chain rule. So I'm going to have to say the cosine of 3x, like that. And then don't forget that I have this 3x in here, and so then I am going to have to multiply by the derivative of that, which would be 3. So if you look at a final answer for this someplace, we can combine this a bit. I can multiply that 3 and 2 together. So I'll have 6, and I might put the cosine of 3x in front there also, and then all of that times 1 plus the sine of 3x. So that's kind of weird in that you have to do that outside first and then the inside, and sometimes you have to repeat that inside a couple different times like we had here. But again, not to worry, we'll be practicing on this stuff in class quite a bit, and you'll get this down really well. Alright, here's kind of a new thing that I wanted to go over and give you a little bit of information on. We have some things in math called parametric equations. We haven't done much with that in any of your classes thus far. And if you think of the word parameter, a parameter is just kind of a guideline or a type of restriction or something like that. Usually it's the variable t. So we'll still have our x and y, but then we introduce this other variable t that acts as a parameter of the equation. So anyway, what we're going to have here is a parametrized curve, and this x of t and y of t is differentiable at t if x and y are differentiable at t. So don't worry too much about that. Essentially what we're going to be doing, though, you're going to be given some function with x, some function with y. There's this variable t in here. We'd ultimately like to try to find that derivative, dy over dx. But I just wanted to show you here where this is coming from. Dy over dx, we can write that as dy over dt because we'll be given some equation with that. Dx over dt, we'll be given some equation with that, with a x and a t in it. We want to find those derivatives. But just why this works out is, remember that when we divide fractions, we end up multiplying by the reciprocal. So in this case, I have my dy over dt. I'm going to multiply that by dt over dx, because dividing is like multiplying by the reciprocal here, right? And notice what happens. The dt's cancel out, and so I do end up with that dy over dx, which we affectionately know as the derivative. So we're going to do a problem like this. We'll be practicing on these in class some too. Again, don't expect you to totally get it when we first look at it here, but we'll be doing a number of these kinds of examples. Alright, so here's our problem here. Find the equation of the line tangent to the curve at the point defined by the given value of t. So again, this is a little bit different because we have an x equals equation, we have a y equals equation, the variable there are t's, and we're given a certain point where we want t to begin with here. So, thank you, there's Mr. Fran giving me some more money, which I always take. So, alright, and so we're going to try this example here. Remember, our first idea here now is to try to find the derivative of x. So certainly dx over dt. We've mostly done dy over dx because those are the two variables we've had, but this will just give us a little bit of experience with a different variable. So dx over dt, I think you can see, will just be 4t. 2 times 2, and then the variable decreases by 1. Now let's look at dy over dt. That's my second equation there. And as we can see from that, the derivative of that one is just going to be 4t cubed. Now when I try to find this dy over dx, I'll kind of combine these here a little bit. Dy over dx is going to be this one, basically, dy over dt over this one. And I think you see what we're going to get here. So we put the 4t cubed over 4t like that. And certainly a lot of the t's will cancel out, the 4's will cancel out, and I end up with simply t squared. Now, what is that again? Well, that's my dy over dx. We know that as the derivative. In this particular case, we know it as the slope. So the idea here then is that when t is equal to -1, then this dy over dx, which we know as the slope, will be -1 squared, which is 1. Why do I square it? Well, when I figured out my derivative here, it was t squared. So at that particular t value, then I can just square it. So that is the value. So that's saying that the slope at -1, which is what we want, is actually +1. Okay, now we actually need to get to the equation part. I'll change colors here to help us out. And we'll do that in a variety of ways. So notice it gives us particular x values, but we do know that t is equal to -1. So if I just plop that -1 in place of t here, let's see what we get. So -1 squared is 1, 2 times 1 is 2, 2 plus 3 is 5. So x is 5, and y is, if I put -1 in place of that, -1 to the 4th power, I believe will give us +1. So this is saying that my particular x and y value, when t is equal to 1 here, will be 5 and 1. And that'll help me when I try to write an equation, which is what I'm ultimately going to do here. I'll change colors once again to help us out here. Now let's just use, for variety's sake, let's use the point slope form for an equation. So y minus y1 equals m times x minus x1. This will just help us so we don't need to figure out that b value, the y-intercept. Now we can consider these two values as x1 and y1 essentially. And remember that my m in this particular case can be considered to be 1. That's my derivative. So let's just plop in some stuff and see what we get. So y minus y1, well, the y1 is 1. Here's m, I put a 1 in for that. The x stays there, and the x1 in this case is 5. Almost done here, gang. So this is y minus 1 equals, well, x minus 5. Add 1 to each side, and I get y equals x minus 4. That's my final answer. So again, what is that? That's an equation of a line that is tangent to a curve at this particular point when t is equal to -1. Again, we've done some stuff like that before. This just adds a wrinkle to it when we have these parametric equations with that extra variable t. All right, and finally, here's just a little thing helping us remember the chain rule here, in case you like to wear your chains while you do the chain rule. That'd be really fun too. All right, so we'll see you dogs in class. Bye now.